All right. We got a little bit of atomic structure talk. During the beginning part of the semester. Now we're going to go into a little more depth. And the reason we want to investigate the structure of the atom a little better, a little more thoroughly, is the way it informs how atoms react to one another when they try to form bonds. So in this discussion of atomic structure, we're not going to ignore the nucleus, but we're going to spend most of our time focusing on the electrons. Because when two atoms come together to form a bond, the first thing they see is electrons, and that's where the bonding occurs. And then we're going to look at that, that type of structure for the atom, the electronic structure, and how does that help us actually, how does that figure into the periodic table? The periodic table is built so that you can deduce the electronic structure of any atom from the element's position in the table, with a couple of exceptions. Okay, so let's proceed. How do we know anything about the atom? We can't see the atom, and much less see the electrons that are in the space around the atom. The information that we get from the atom comes by way of light, electromagnetic radiation. And from a human perspective, that means colors. But from a scientist's perspective, that means more than just colors. The electromagnetic spectrum is extremely broad, and various sections of that spectrum give us different types of information about the atom, about molecules, about individual bonds, as a matter of fact. And we see evidence of the activities within the electronic structure of atoms in the display of colors in fireworks. Some atoms will be, let's see. Oh, okay. You know, I got a better slide set than this one. Let me pause. Let me stop the share and get a better version of this particular. Hold on just a second. I think it'll be worth the wait. Let's close that and let's open a different one. I thought I had put modifications in both Southern's course and in my course at New River. So let me go into my New River stash and pull up that set. Now, the only disadvantage is you won't have access to it yet. I will update the PowerPoints in Brightspace. I thought I had already done that, but apparently not. Okay. Here we go. All right, you can't see what I'm doing yet. See, I'm going to close that one. And this is the one I want to share. So let me go back to Zoom meeting and share. Come on. There we go. All right. Make a slideshow. Come on. There we go. Yeah, this is a better set. Okay, so I won't rehash that part of the presentation. In fact, indulge me for another second. This way I won't have to be stepping back to the computer every time I need to switch slides. There we go. Okay. So why do we get colors? Well, based on two facts. One is you have different elements in the fireworks. Some elements give different colors than others. You probably already know that. But there's another ingredient that's required that we often overlook because it's sort of accepted in fireworks. It's that big bang. It's the explosion. It's the energy that's released that excites the atoms that give us the different colors. And now we want to know, why does sodium come out kind of yellowish orange and say strontium comes out hot pink? And you get different colors. These are elements that are blown through torches, and you can see the difference there in their colors. These are questions that we have to ask on the way to getting answers about the electronic structure of an atom, believe it or not. We're headed there. We also have a question that's kind of on the side. Why do these colors, there are certain colors in a flame when you excite the elements directly with heat, and if you put that same element in aqueous solution, you get a different color, right? So those are all questions that can be answered by the electronic structure of the element in one case, and with the association of the element with other things like water molecules. That tells us how the electrons move and between different energy levels. That's where we're headed. Okay. This is just a side note. We all know that, well, most of us, I guess, know that when blood streaming out of an artery is going to be brick red. It's going to be red because the oxygen combines with the iron in the hemoglobin to give you that color. It's kind of like rust. But if you extract blood from a vein, it's going to be kind of a dull, maybe even a purplish color, because it has less oxygen, almost no oxygen in it. Right? So that the color of the iron is different based upon its association with oxygen. And I'll make this quick. I did my master's thesis on processing waste from crawfish producers. They would boil the crawfish, extract the tail meat, and package it and freeze it for export all over the world. And they have all this waste. About 15% of the weight of a crawfish is its tail meat, and the rest is discarded, almost all of it. I mean, they take some of the hepatopancreas out of the shell and put that in a separate bag. And people that have been doing this from birth, boiling crawfish and eating crawfish, will do what they call suck the heads. You pop the tail off and you suck that yellowish green stuff out of the body, and I never did learn to do that. But they say it has a flavor that's desirable. Anyway, you know that the crawfish has a red color in its carapace. And that color is primarily due to a compound called astaxanthin. And there is the structure. notice it has all these double bonds. It's double bond, single bond, double bond, single bond. Those are called conjugated double bonds. And that has the effect of the more of them you have strung together, the lower the color comes in the spectrum. So if you start from violet, move down through the blues and the greens and the oranges to the reds, the more of those double bonded, those conjugated double bonds, the further down you get in the range toward the reds. And that's due to the way the electrons move between energy levels. Okay, so if we're going to learn something about the elements, whether they're here on Earth in the chemistry lab or they're a billion light years away in some far-off galaxy, the information comes to us by light. So we need to know something about light and understand how light works. You need to know 3 different numbers, sometimes variables, in order to define light. One is wavelength, and we use the small Greek letter lambda for wavelength. Wavelength is the distance between, if this is our sample wave, right? The distance between here and here is 1 wavelength. So it's the hump on this side of the mid-range. You don't go from this hump to that hump, you go from this hump to that hump. Or you could go from where it comes up across the line and up across the line again. Same thing. That's a wavelength. And the standard unit for the wavelength is the meter. That's the SI unit for wavelength is the meter. Right? We use other units when they're convenient, but that's the fundamental unit. Frequency. It's often given that kind of a curly F, but it can also be that Greek letter. It's called nu, pronounced nu. That's frequency. Frequency is the number of wavelengths that pass a fixed point in 1 second. So often we call it cycles per second. But cycles is not a unit of measure. It's stuck in there so that we understand what we're measuring. But the actual units of measure for the frequency would then be reciprocal seconds. And that's also given another unit in honor of one of the pioneers of electromagnetic radiation, Hertz. Right, so the Hertz means reciprocal seconds or cycles per second, in case you need to do some calculations and cancel units. And then the last one is the speed. The speed of a wave will vary. And it depends on whether you're talking about sound waves or light waves or whatever else it might be, seismic waves. It's the how many meters this hump travels in 1 second. Right. So it's going to be in units of meters per second. And for the speed of light, we're given this special symbol. Normally we would just say V for velocity. But for light, we say little c, and that's equal to 2.9979 times 10 to the 8th meters per second. That's the speed of light in a vacuum. Okay. Now, believe it or not, light will travel at different speeds depending on the medium. If it's in a vacuum, that's the speed. If it's in air, it's very, very close to that. And for all intents and purposes, we can use that value for traveling through air. But if it travels through something like glass lenses, it actually will slow down. So what does that tell us about light? That tells us that light interacts with matter, right? If it didn't interact with our glasses, it'd go through and the measured speed would be the same as a vacuum. But if it stops momentarily to interact with molecules in the glass or whatever the medium is, then it has to slow down to do that. Okay, so these three factors, the constant, we would call this a constant for a vacuum anyway, and the variables, lambda times frequency. So that's their relationship. Wavelength times frequency equals speed of light. And if you check your units, this is supposed to be meters per second, correct? This is in meters. This is in reciprocal seconds, which means it's in the denominator. So the units match. And if you do any calculations, then you need to match those units up. Like any of the other equations we've done, you can't just throw them in there. No matter what their units, they have to match. Okay, so that says something about the nature of light. And this is an artist's idea of what you're looking at. Notice one thing, I shouldn't have erased that. C equals lambda times frequency. Notice that this is like Boyle's law. Pressure times volume is a constant. This is wavelength times frequency is a constant. And anytime you have a product of two variables that's equal to a constant, you have an inverse relationship. If this one gets bigger, that one has to get smaller, and vice versa. So if you look at this representation, you see that the wavelength for this first one here, the wavelength for that first one is large. And the frequency is small, 4 cycles per second, or 4 hertz. But if the wavelength gets smaller, then the frequency gets bigger, right? Gets smaller again, frequency gets bigger again. That's an inverse relationship. All right, here is the entire electromagnetic spectrum. All the way from the lowest energy side on the right, the radio waves, up through visible light and on to gamma rays. Gamma rays are the most energetic light rays in the universe. And certain types of gamma rays, if they're directed from a distant object, from some astronomical event, if they're directed at Earth, they could strip the Earth of its atmosphere, and that would be the end of Earth. Fortunately, we've never experienced a direct hit that we know of. Okay, back to the topic. Notice that visible light is only a very narrow range of all the possible electromagnetic radiations described. And it occurs between 4 and 7 times 10 to the minus 7th meters wavelength. So we could say this four times 10 to the minus 7th meters up to 7 times 10 to the minus 7th meters. That's kind of hard to work with. I mean, if we need a more convenient scale, a unit of measure that allows us to do away with the scientific notation. So we use the nanometer. So how many nanometers is 4 times 10 to the minus 7th meters? Well, the nanometer is 10 to the 9th. 10 to the 9th nanometers equals 1 meter. All right, so if we apply that as a conversion factor, we get 400 nanometers to 700 nanometers. Now it's more convenient to discuss wavelengths in terms of nanometers, but still, when you're doing the calculations using this equation, they have to be converted back to meters. All right, So we've got this, the visible lights, right? Everybody remembers your jingle, Roy G. Biv. That's not a jingle, it's an acronym. Roy G. Biv, red, orange, yellow, green, indigo, green, blue, indigo, violet. But that's not everything. If we go to a longer wavelength than red, we get to infrared. And we call it infrared because it's underneath red. And that's not in terms of the wavelength, because the wavelength of infrared is longer than red. Right? So why do we say infra? We say infra because it's less energy. It's lower frequency. Right? And there's a direct correlation between frequency and the energy of that particular wavelength of light. We're going to explain that in just a minute. So that's infrared. Longer wavelengths, you get the microwaves, right? Just like a certain wavelength of microwave is used in the microwave oven to heat your food. But it's also used in communications. Actually, there are lasers that emit microwave radiation. And even longer wavelength is predominantly for communication and for special types of ranging, like radar. FM, shortwave, AM are the longest wavelengths, up to several meters distance between the peaks. If we go to higher energy or higher frequency, shorter wavelengths, from the violet we go to ultraviolet. And then we move with even higher energy to X-rays, higher frequency, shorter wavelengths, and ultimately to gamma rays. All right. So where does all that energy come from that's packed into those light waves? It's got to come from somewhere, right? Because we can't create energy, we can't destroy energy. Conservation of energy is an absolute law in the universe. So we need energy from somewhere. It's got to be converted from something else into light. And it could come from several different sources, right? Light bulbs. We used to have light bulbs that converted electricity in the socket into light simply by heating up a filament, right? Just like Edison invented the incandescent light bulb. That's kind of what we're doing with this pickle. We're running a high voltage, high amperage charge through that pickle, and some of the energy is being converted into light, but a lot more of it is being converted into heat. So my guess is that pickle doesn't smell too good. Let's see. Oops, I went backwards. Sorry. There we go. A little bit of a history lesson would be instructive. All right. In the middle of the 19th century, there was an effort by many scientists, and one finally came up with a solution. His name was James Clerk Maxwell. And what Maxwell did was he treated light as a wave, which was the common understanding for light at the time. And he developed these series of equations that completely described light and its behavior. Not just what its color is, but how it behaved when it traveled through various media. And these equations work perfectly well for electromagnetic radiation as long as it is behaving as a wave, right? And there's certain characteristics, certain processes that indicate to wave behavior. We'll discuss those in just a minute. And those equations still work just fine. At the dawn of the 20th century, scientists believed that they knew all there was to know. The only thing left to be done in the future was to refine those facts, predictions, equations, whatever the case may be. They couldn't be more wrong, because just around the corner was the discovery that light doesn't necessarily behave as a wave. Under some circumstances, it behaves as a particle of matter. All right, so that's where, and the big controversy erupted over that. What we refer to now is the quantum nature of light. Quantum refers to packets. A quantum of light is a discrete packet of energy that travels from here to there. And some of the first research that was done on it was in reference to black body radiation by Max Planck. Black body radiation simply means that if you have an object that does not emit its own light, right, it's a black body. Think of a big chunk of coal or a chunk of compressed carbon. How does it emit light, right? Black body radiation. It's going to emit light. Well, it doesn't emit light until you heat it up. So if you heat it up and the temperature, as the temperature increases, you can measure a change in the type of radiation that is given off by that black body. And the hotter it gets, the bluer it gets. In other words, it moves through the color range. It moves through infrared, through blue, through green, through orange, through reds. Excuse me, I'm going the wrong direction. As you heat it up, it goes from red, the red side, and it goes up through the blues and even into the ultraviolet. Now, how do we use that today? Astronomers use it all the time. They classify stars according to their color. And the color is an indicator of the temperature at the surface of that star, based upon this black body radiation research and the equations that come from it. So when an astronomer measures the spectrum of a star, they're able to say what color is that star, what is its radiation, what is its temperature based upon that radiation. Okay, in addition, Planck did some work that developed an equation where we equate energy with frequency. So what he said was the energy that is carried by that packet of light is equal to some constant value times the frequency. So energy is proportional to frequency, and all you need is a constant of proportionality to make the units jive. Now that value, Planck's constant, is given in these slides. It's also at the end of your review document in useful information, so you don't have to memorize it. Okay, and that's a direct relationship. Right? If we move this one over here, we got a quotient equal to a constant. Remember, quotients equal to a constant always mean that the variables are directly related. So as frequency goes up, energy goes up. But you may not know the frequency. Maybe you know the wavelength. Well, all we have to do is use this relationship, right? Lambda times nu, solve for nu, like that. Substitute that right there, and you got that new equation. And there's Planck's constant. See, it doesn't make any sense standing out there all by itself. 6.626 times 10 to the minus third joules seconds. The reason it's like that is to make the units jive. Energy is going to be in joules. Frequency is in reciprocal seconds, right? Oops. So this one has to be in such a way that it has joules and seconds so that the seconds cancel and leave joules on both sides. That's why it's that way. And then the number is just to take the frequency and make it jive with energy.
Everybody knows Albert Einstein for his theory of relativity and the Nobel Prize he won for it. He also—
What? I didn't win the Nobel Prize for relativity. I won it for explaining the photoelectric effect.
Right, of course, sorry. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is it? Okay, let's rewind a little. Newton had thought light was made of particles, and his rival Hooke had thought it was a wave. And when technology advanced enough, some experiments proved Hooke was right. That proof, and Maxwell's equations describing light's behavior as a wave, made the debate die down, until the photoelectric effect was discovered. When light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened for light of some wavelengths. For others, no electrons jumped at all. Einstein was bewildered. The photoelectric effect should work regardless of the type of light. If light wasn't made of particles, and now it turned out that it couldn't be made of waves, what was it made of? After much reflection, he formulated a new hypothesis combining the two previous ones. What if light were made not of waves or particles, but of both? That is, what if light were made of wave packets? That concept, which we now call photons, allowed Einstein to write out equations that explain the photoelectric effect in 1905. This consolidated the idea that light can sometimes be described as a wave, sometimes as a particle, and sometimes as either. It was a revolutionary view, and it opened the field for quantum physics. Robert A. Millikan, an American experimental physicist, was unconvinced by Einstein's conclusions, so he set out to prove him wrong by carefully measuring the photoelectric effect. However, years later, Millikan ended up proving Einstein right, and they were both awarded the Nobel Prize in Physics.
Okay, so the photoelectric effect. It's simply the ejection of an electron when light of a particular wavelength strikes a metal and ejects an electron. That's the photoelectric effect. Now, there's more to it than that. What they described is that it was discovered that it didn't matter how bright the light was. In other words, the intensity didn't matter. All intensity does is increase the number of photons of that particular energy striking the metal, and that did not give the electrons enough energy to be ejected from the surface of the metal. What mattered was how much energy just each packet contained. And there was a minimum amount, depending on the metal, right? Magnesium would be one, zinc would be a different one, copper would be a different one. Each one would have a different critical energy or critical frequency at which you would start to get electrons ejected. Now, if the frequency were higher than the critical frequency, then that would be enough energy for the electron to leave the surface, and then any leftover energy was translated into the kinetic energy of the electron. It would just move faster. Okay, so what was happening was, during the beginning of the 20th century, scientists were beginning to realize that light was a much more complicated concept than was previously thought. Sometimes light behaves strictly as a particle. Sometimes it behaves strictly as a wave. And for the photoelectric effect, Einstein proved that it had characteristics of both at the same time. This threshold frequency, I said critical. The proper terminology is threshold frequency. And that looks like a V, but it's really one of these right here. Right. That amount of energy, h nu, which is equal to energy, remember, is required to eject an electron. That minimum threshold frequency will give you an electron that's free from the atom, but it has no kinetic energy. It's just removed from the atom. Anything above that will start to give it some velocity. And remember, Robert Millikan, who the video explained, tried to disprove Einstein's theory, came to support it. He was the same one that did the oil drop experiment and determined the mass of individual electrons. So that seems like a contradiction. I mean, if the electron has mass, well, wait a minute, we're talking about electrons and not light, excuse me. I'm getting my topics crossed. They will come to meet later. Okay, so below this threshold frequency, no electrons are emitted. It doesn't matter how intense the light is. If light were strictly wave and nothing else, then more intense beam should eject electrons. But as it turns out, once you've met that threshold frequency, the more intense beam, all it does is eject more electrons. And number 4 says what I said before. Any leftover energy beyond the threshold is translated into kinetic energy for the electrons. Right? So the conclusion is that electromagnetic radiation must arrive at the surface of the metal as discrete packets, as photons. And that there's a minimum amount of light contained in that photon to eject the electron. And that extra energy overcomes the atom's ability to hold the electron with its positive nuclear charge. By the way, any photons that don't have enough energy, right, their threshold frequency is not met, it's too low. That energy is not lost, right? We're still conserving the energy, but since it cannot eject the electron, all the energy that it possesses is either one thing is either reflected or it's absorbed by the metal. And if it's absorbed, we call it thermal photons because it's absorbed as heat. Okay, we covered that one already. And we covered that one already. Okay, so what does the photoelectric effect tell us about the structure of the atom? The interaction between light and the atom occurs with the electrons. Right? The nucleus is just there as like an anchor. That's the center of the atom. But the interaction between the atom and light is with the electrons. And if you have enough energy, you have the nucleus here, and you have an electron out here somewhere. If enough energy comes in, then it promotes this electron to a higher energy level. And notice that lower energy levels are closer to the nucleus and higher energy levels are further from the nucleus. And that's based upon the fact that you have to add energy to the electron to promote it, to move it further away, because it's being attracted by protons. So you got to give it enough energy to get away from the protons. So that's why these are higher energy levels than these. Ultimately, if this has enough energy, then this electron will be promoted to a distance of infinity relative to the nucleus. In other words, it's not attached to the atom anymore. That's the whole concept behind the photoelectric cell, where we take sunlight and convert it directly into electricity. That's the process that happens. Okay, second, I sort of alluded to that one. The absorption of this photon is directly related to the movement of an electron in energy levels around the nucleus of the atom. So we have various energy levels like that, and the electron will be promoted from one to the other, depending on how much energy is provided by that photon. Now, if it only goes between these energy levels, right here, it has to be exactly the right amount of energy, right? Anything less, anything more won't do any, it won't promote the electron. It has to be exactly the right amount to go from this level to the next level, or that one to another level, whatever the case may be. It's kind of like tuning. The atom is tuned, the electron is tuned to certain frequencies of light. I mentioned that already. It's promoted to infinity. And there we said that again. And by the way, kinetic energy implies that the photon has mass. Right? If the photon can impart speed of any kind to an electron, then it's got to convert that energy that it has into kinetic energy for the electron. And if you take the simplest possible example, right, if this is the electron and this is the photon, when it bangs into that electron, it transfers energy to the electron. That's why we're saying that that photon has mass. And it took Einstein to make the relationship. Right. All he had to do was come up with this equation, a very simple equation. Right? Energy and mass are equivalent. And the conversion factor is the square of speed of light. He proposed this equation in his theory of special relativity that he published in 1905. There were just a few years in there where Einstein was working in the patent office in Bern, Switzerland. And he was so brilliant, he could review the stack of patents that he was assigned in just a couple of hours, say in the morning. And then he spent the rest of the day just sitting there scribbling at his desk and going through theoretical mind gyrations and coming up with this stuff. He published several papers while he was there at the patent office, and one of them was special relativity. And in that paper, he proved that light and mass are equal. I won't go into the nuances of rest mass versus relativistic mass, but they are slightly different. In other words, I'm standing right here and I'm theoretically not moving. So I have a rest mass. But if I'm moving at a significant fraction of the speed of light, I have a different mass, a relativistic mass. And that's what we're talking about with electrons. Okay. Now, if you know anything about physics, you know that there are basically two camps. There are the theoretical physicists, and all they do is propose things and write equations and argue amongst themselves. Well, they do more than that. They publish papers. And then it's up to the experimental physicists to prove or disprove their results of the physical. And sometimes the theoretical physicists feed off of the results of experimental physics results. So as a point, Einstein proposed that if his theory of relativity was correct, then the light coming from a distant star passing close to the sun would be bent. And that would make the star that it came from look like it was over here and not over here. So that was eventually confirmed during a total eclipse. That's another story. So light has a dual nature. It's both wave and particle, depending on the application. Right? They're both correct. Now, what are the various manifestations of light that support one over the other? Well, if you think of light as a wave, then it should be diffracted. So diffraction is a process wherein, say if you have a light beam, if light were particles, they would travel in a straight line like this, right? Light would travel in a straight line, and if light were a particle, under these circumstances, then it would strike this detector over here straight like that, and this would be a shadow. It'd be a stark difference between light and dark, just straight across. And if there were more of them, there would be light here, so forth. But it's not. What happens is this edge serves as a point source for a wave. So light's coming along here as a wave, and when it strikes this and gets to that edge, it starts propagating from that edge like a wave. And in this illustration, that wave, which looks like it might be ripples on a pond, hits this barrier, and the slit in the center serves as a point source for the new wave. That is diffraction. Refraction, which is the next characteristic of a wave, is demonstrated by a glass plate or a lens. So if we have glass here and air here, then the wave is coming in. And if we use a ray diagram, we call them a ray diagram for light, and here's the vertical, the normal to that surface, what happens is the light beam bends, right, toward the more opaque. There's a term for it. It's the one with a larger index of refraction. So why is that? Well, the only way we can explain it, right? If light were particles, it'd just keep going straight down here like that. But if light is a wave, what happens is the wave comes in like this, and when the one edge of the wave strikes that glass, that part of the wave slows down. Right? So instead of coming out like this, it comes out like that. And then the next wave may come along like this, and it comes like that. So eventually, you get the wave changing directions, right? Like that. That's characteristic of a wave, and it's called refraction. And it's what makes corrective lenses possible. Support for the particle nature of light is, we've discussed already, is the photoelectric effect. You can't explain it with waves. Only as a particle can it be explained. Well, actually, you combine characteristics of wave and particle, but it's still, the light has to be in a packet to do it. Okay. Now, what does all this have to do with the atom? Right? We've done a lot of preliminary work here to allow us to now start talking about the nature of the atom. And we're going to start with the very simplest element, the hydrogen atom. And before we do, let's describe the difference between types of spectrum, right? I don't know if you've ever done it, but I was curious from an early age about using prisms, right? You have light coming from the sun and you use a prism, and wow, you get colors coming from the prism. So that's a manifestation, an artifact of refraction, because light is refracted through this various medium differentially. It's refracted more for blue light than it is for red light. So you get the various colors bending, but they bend at different angles based on their wavelengths. So you get this spectrum. Well, if you do that for light from the sun, you get a continuous spectrum. You get every color in the rainbow, right? But if you do it from hydrogen that is in a container, and we spark electricity through it and excite it so that it gives off light, then the hydrogen only produces, through that prism, produces a line spectrum. It produces 4 visible lines, right? Now, the natural question is, why does it do that? Right? If light were a wave, we would expect a continuous spectrum, just like we get from the sun. Okay, so there's your continuous spectrum. That video doesn't work anymore, but I like the picture, so I kept it.
The discharge tube is filled with hydrogen gas. When a high-voltage electrical discharge energizes the gaseous atoms, light is emitted only at specific wavelengths. The emission spectra obtained are called line spectra, due to the appearance of bright lines. In the hydrogen emission spectrum, there are 4 lines in the visible region. A purple line at a wavelength of 411 nanometers, a dark blue line at a wavelength of 434 nanometers, a green line at a wavelength of 486 nanometers, and an orange-red line at a wavelength of 656 nanometers. Let's look at the electronic transitions responsible for the observed line spectra. When an electron drops from a higher energy orbit to a lower energy orbit, a quantum of energy, a photon, is given off in the form of light. During the electronic transition shown, light is emitted in the visible region of the electromagnetic spectrum. You may click on the buttons to review each of the electronic transitions individually.
Okay. I wrote these down as the video was playing, just so we could talk about them. These are 4 visible lines in the hydrogen spectrum. Now, if we have our sufficient detectors to peer into the ultraviolet or the infrared, we will pick up other lines that are based upon other transitions of these between these energy states. So between and we're gonna describe exactly what those N numbers mean in just a few minutes. But for now, just look at them as different energy levels. Notice that the lowest energy level is 1. That's not right on the nucleus, but it's close. Right? No electron's going to be right on the nucleus. It'll be at a certain distance. And then there's a jump from 1 to 2 of a huge amount. And then the jumps get smaller as you go from 2 to 3, and then 3 to 4, and 4 to 5 to 6. So that's why if the jump is between 6 and 2, there's not quite as much energy transition. In other words, when you add energy to the electron, it jumps to the next level, or to a level. And if it goes from 2 to 3, you put in less energy. If it goes from 2 to 4, you put more energy, more energy, more energy up to 6. But when that electron drops back down from 6 to 2, it gives that energy off with the same wavelength as it took to make the jump in the first place. Okay? So it's like a revolving door. It goes both ways. And this is the higher energy. The shorter wavelength, the higher frequency is more energy. So energy is high here, lower, lower, and lower. That's why we say that the blue end of the spectrum is higher energy than the red end of the spectrum. In this case, kind of a red-orange. Okay, so I said this before, but I'm going to say it again. Only certain energies are allowed for the electron in the hydrogen atom. If you try to promote an electron with anything in between here, 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 it won't happen. Or if the electron makes these jumps, you always get those single lines that are characteristic of the hydrogen atom. And in fact, this is the way astronomers identify elements in other suns and other atmospheres of exoplanets and so forth. They look for either emission of the light at a given wavelength, which is characteristic of an element, or if you shine light from behind and it travels through a cloud of atoms and you find a dark line where there should have been one in a continuous spectrum, then you know that it was absorbed by a certain element. You can also identify them that way. And a spacecraft that we've sent into the outer planets will, once it passes the planet, will turn around and look back through the atmosphere of that planet or moon toward the sun and take a spectrographic reading of it and look for dark lines that tell it what elements are in that cloud or in that atmosphere. That also tells us confirms that the energy of the electron is quantized just like light is quantized. In other words, these electrons can only move between these particular energy levels, and they cannot occupy anything in between. It's forbidden. Okay. Why is it significant that the color emitted from hydrogen emission spectrum is not white? Well, let's see. They're going to answer it for us. Oh, if the levels were not quantized, we'd probably see white light from every element. It wouldn't matter. And how does the emission spectrum support the idea of quantized energy? Since only certain colors are observed, this means that only certain energy levels are allowed. You don't see any colors in between, here, here, and here. You only see those specific colors. That means the energy levels are fixed and quantized. Right? There's no in between. It's either you move from here to here or you don't move. Okay, so now let's take this information and start to construct an atomic model, particularly an electronic model for the atom. And we start with the Bohr model. Niels Bohr, he was a Danish physicist, and he was early 20th century, as were many of the big brains of those days that were working on what's the nature of the atom. These are the same people that made it possible for us to develop atomic energy and the atomic bomb, for that matter. So what Bohr said was he used the planetary system, the sun's planetary system as a model. And he said, okay, suppose that the nucleus is like the sun. Okay, there's your nucleus. And the electrons are moving in circular orbits around the nucleus at fixed distances corresponding to their energies. Right? This would be orbital 1, this would be orbital 2, 3. We could go on up to 6 or higher. That's where those ends are. They represent energy levels around the nucleus. The n equals 1 for the hydrogen atom is known as the ground state. That is lowest possible energy for that first electron. And hydrogen only has 1 electron. If this one is filled and the outermost electron now has to occupy this level, then that is the ground state for that one. So 1 will be hydrogen, 2 would be helium. Well, this energy level N. And this is equal to N. This is equal to N. Then where does lithium go? Lithium's got 3 electrons. Well, it has to go out here. So you have 2 electrons there and 1 there. Okay, so these N numbers represent energy levels. And this is a better representation of the energy levels. It's a huge jump between 1 and 2. And then the jumps become lesser and lesser. Okay, here's another way of looking at them. What Bohr also provided was a way to calculate the energy of the transition. He provided equations along with his model that would calculate the energy of transition, or actually first the energy of the level itself. And then if you know the energy of this level and the energy of that level, then the amount of energy it took to transition up or the amount of energy given off transitioning down could be calculated. You just subtract one from the other. Okay, so here's how Bohr calculated the energy level for any electron based on the N number. Okay, this value right here is simply a proportionality constant. And what you need to know here is N equals the energy level, and Z is the same Z we've talked about from the beginning. It's the number of protons, the atomic number of the atom. Okay, one very important caveat to using this equation. Z can be any number for any atom on the chart, but the equations only work if your atom is like hydrogen, 1 electron only. If it has 1 electron, then you can use the equation. So if Z say helium, right? Helium has 2 electrons, right? It's got to lose one of them. So if it loses an electron, now it's a +1 ion. That's like hydrogen, electronically speaking. Lithium has 3 electrons, so it would have to be a 2+ ion to be like hydrogen. So you get my drift. The higher you go, the more electrons you have to remove before you can use this equation. So that was one of the shortcomings of the equation, was it didn't work very well for anything but hydrogen. But that would tell you the energy at that level. Okay, and that's the legend defining what each one of those values represented. All right, so for the hydrogen atom, you just substitute 1 for the Z, and that gives you the energy for the hydrogen at any level n. All right, so if we take those 2 equations and we say, remember, delta E, a change, always is final minus initial. So if the final is down here and the initial is up here, they go in those particular places. But if you're going the other direction, if the final is here and the initial's here, they're switched. And that actually changes the sign on the value. And you can tell from the sign on the value whether you're moving up or down. Right? And if we simplify this equation, all you have to do is factor out common factors. Minus 2.178 times 10 to the minus 18th is occurring in both of them. So you factor it out, and that leaves you with z squared over n squared final minus z squared over n squared initial. And that equation will tell you the energy transition from one level to the other. And of course, if it's hydrogen, you just put a 1 where the Z is. Okay? So, for example, if we have a hydrogen atom where the electron transitions from 5 to 2, right, goes from 5 out here down to 2, then it should give off energy. Okay? And we're given the wavelength. It's a blue wavelength, 434. It's this one. Okay? Since we know the wavelength, we can calculate the energy of that transition, right? All we need is Planck's equation, or I think that's right. No, it's the other way around. Excuse me. Yeah. There you go. So you can use that equation to determine the energy, and you can also use Bohr's equation to determine the energy and just see if they match. So if we use Bohr's equation, the transition tells us that the energy for that particular wavelength of light should be minus 4.57 times 10 to the minus 19th joules. Okay, the minus means that energy is leaving the atom, right? Remember our, well, maybe, yeah, we've talked about thermochemistry. So if this is the system, energy is leaving it, it's a negative value. Right? So it's consistent with that model. Okay, if we take the wavelength of light and use Planck's equation, then we can calculate how much energy that light beam has in it, that photon has in it, and it's 4.577 times 10 to the minus 9 joules. And the values are almost identical. The difference is that negative sign. This tells you which direction the energy is moving, right? It's being emitted from the atom. This just tells you, you don't know where the light beam came from. That's how much energy it has. And they're almost identical. Okay, so the Bohr model correctly fits the quantized energy levels for the hydrogen atom. And based on these N numbers, postulates only certain circular orbits that are allowable around the hydrogen atom. So as the electron moves closer to the nucleus, the energy becomes more negative. So think of it this way. If the electron is coming from infinity, and infinity is zero energy, then as it gets closer, it's giving up energy, right? It's losing energy as it approaches the nucleus. That means energy is leaving the atom, and that's a negative value. So the more negative the value, the closer the electron is to the nucleus, and the more negative is the value of energy associated with that orbital, with that particular position. Unfortunately, Bohr's model is not correct. It was a good first step, but it only works for hydrogen or hydrogen-like atoms, only one electron. It also postulated that electrons move around the atom in circular orbits, which they don't. And one reason we know is if the electron, which has mass, is moving around this orbital, then as it changes direction, it has to bleed off energy to do it. So the electron should eventually spiral into the nucleus, but it doesn't do that. Okay, what's the color of light for each one of these? We've gone through that already, so I'm not going to spend a lot of time on that one. That's the minimum amount of energy is from 3 to 2 for the hydrogen atom. Actually, that's the minimum that we can see. There are cases where there is less energy being emitted. You could have a transition from 6 to 5 and give off something in the infrared or something we can't see. Okay, we're about halfway through. It's almost 3:30. I think I've got time to finish before 5. Yeah. This next principle, the Heisenberg uncertainty principle. Werner Heisenberg was another brilliant scientist, and he, in his work, which was rather broad, he came up with this idea that informed us about the weaknesses of Bohr's model. What he said was, there are 2 important factors that are required to describe any particle in the universe. Its position and its momentum. Its position is, in this equation, delta x. Delta x means a change, so I'll get to that in a second. And its momentum is mass times velocity. That's not nu, that's v, that's velocity. And he says, when you multiply these 2 differences together, they have to be greater than or equal to Planck's constant divided by 4 pi. Okay, what does that mean? What it means is there's always error in any measurement. So the measurement error of position, right? We don't know exactly where something is, but we can get pretty close on some things. Like me, I'm standing right here. You know my position just by looking at me. Momentum is mass times velocity. It's given the symbol rho. That's a Greek letter. But if we're talking about a single particle or a single mass of any size, and we don't change that mass, then this is a constant. And the only thing that's going to change is the velocity. So that's why often you'll hear Heisenberg's uncertainty principle as you can't know both position and velocity, which means energy, right? Kinetic energy. You can't know kinetic energy of the particle and its position with any degree of certainty if the uncertainty of the two is greater than Planck's constant divided by 4 pi. Okay, what does that mean actually? Well, if you're really big, if you have a huge mass, then this one is large and this one can be very small. So the error in position is very small for large masses like me. That's why you know I'm standing right here. And you know I'm not moving, right? So with a big mass, the velocity, you can know both my velocity and my position with relative accuracy. But for very small particles, if this is extremely small, then that means that in order to be greater than this value, if this is very small, then that has to be extremely large. That means the uncertainty of the position of the electron, in our case, is unknowable. It's just too big. You don't know where it is because it's so small and moving fast. Okay, so any of the subatomic particles fall in under this principle. They're so small that you can't know both position and energy at the same time. If you fix one, then the other is just too large. If you fix this position as very small, this has to be extremely large, this discrepancy. Okay, so that told everybody, including this list of scientists at the bottom here, that we were facing a dilemma. Which is more important, knowing where the electron is or its energy? And as it turns out, it's more important, not to the exclusion of where is the electron, but it's more important to know its energy with a reasonable degree of accuracy than it is its position. So that means that we treat the energy as the more important factor, and we treat the position as a probability envelope. Like, this is where the electron is most likely to be in this area. Okay? That was Heisenberg. He also came up with a set of equations that set the world on its direction toward quantum mechanics. And there's one particular function in these equations called the psi function. That's the Greek letter psi, psi. And if you square the function, this gives you an indication of the probability of finding an electron in a particular place in space. Notice probability. That doesn't mean it's there. It's just there's a high probability that it's in that space. And in order to make use of that, you'll see sometimes models of atoms with their electron clouds. There'll be these strange shapes. That just means that these are the places where you're most likely to find the electron. And wherever you don't find those shapes, you probably won't find an electron there. This is not a good graph, so I'm going to go to the next one. So if you look at the distance from the nucleus here on this axis and the probability of finding the electron at this distance from the nucleus for any orbital, and we're not saying which one it is, we're just saying the probability of finding the electron at the nucleus is 0. So someplace out here you have a very high probability of finding the electron in that region of space. That's all that graph is telling us. Okay. All right. The point of this slide is that electrons, for our purposes and for positioning them in these energy levels, are best treated as waves rather than particles. When the electron is free from the atom, then the particle nature becomes useful. But when it's attached to the atom and we're trying to figure out how it interacts with other electrons in the atom or between atoms to form the bond, we get more information from a wave function of the electron in that particular orbital. So those equations from Werner-Heisenberg operate on the basis of waves. And one way to look at it is if you have the nucleus here and you have orbital 1 here, then you think of the electron as being a wave at that distance from the nucleus. Okay, that is a whole electron. That solves the problem of decaying orbits, because waves don't decay, not in your typical physical sense. Okay, so usually when you see an orbital map of electrons around an atom, that's the 90% probability that you will find an electron in that region of space. Now, these equations that Heisenberg wrote and have been modified over the years, but they're essentially the same as they were when he started. They've just been refined. They require 4 numbers. Right? These are quantum numbers. And these quantum numbers are assigned to individual electrons in a space around an atom. And they each have meaning inside, sort of a pictorial effect, but they also have physical meanings as they enter the equation to calculate their probabilities of various factors. So let me give them to you. The principal quantum number. This is the same number that Bohr proposed. Starts with 1 and goes whole numbers up. 1, 2, 3, 4, 5, 6, on up as high as you want until you get to infinity, which nobody knows where that is anyway. So the principal quantum number, N, the principal quantum number refers to the size of the orbit and its distance from the nucleus and its energy. So this is size and energy. Right? Any electron that has the same principal quantum number will have a similar probability spread for its size and a similar energy. They may not be exact, but they're generally they're very close. And these can be 1, 2, 3, 4, on up to whatever. Well, let's say n. They go up to any value of n. The angular momentum, or the azimuthal, the angular momentum is given the letter L. Angular momentum quantum number. Momentum quantum number. This refers to the shape of the orbital. Right? Is it spherical? Generally spherical? And it could be a hollow sphere too, right? But it's round. Or is it have lobes on it, or is it a donut, or whatever the case may be? So this refers to the shape. Now, as we proceed, the numbers here, available numbers here, are based upon where you started. Right? If you start with 1, you're limited. If you start with 2, you have a few more options. Start with 3, you have even more options. So they're kind of nested. Right? And they're based upon, they start with 0, 1, 2, on up to n minus 1. Right? So say for example, we have n equals 3. What are the possibilities for L? Well, L could be 0, 1, minus 2. Excuse me, I'm going the wrong direction. No, that's right. 0, 1, or 2 for n equals 3. So you could have n equals 3 and then L equals 0, or n equals 3 and L equals 1, or n equals 3 and L equals 2 for the first 2 quantum numbers. So they're nested. The next one is M sub L. This is the magnetic quantum number. Okay, we got size and energy, shape. Magnetic is direction, orientation in space. And it's based upon the L number. So let's say if we had a 3 here and then we had a 2 here, then the possibilities for this one would be, well, in general terms, it's minus L through plus L. So we could have, for this one, it would be minus 2, minus 1, 0, plus 1, and plus 2. Okay? And the last one's the easiest of all. M sub S. The electron spin. In order to fill the bill for this one, think of the electron as a spinning top. It can either spin clockwise or counterclockwise. And the number that's required by the equations is that it's either plus 1/2 or minus 1/2. So any one of these, whichever the case may be, can have a plus 1/2 and a minus 1/2 in there. So that means you can have 2 electrons here, 2 there, 2 there, 2 there, 2 there. That means at this level, you can have 10 electrons possible. All right. Those are the 4 quantum numbers. N, L, M sub L, M sub S. Now, for the L's, when we start writing electronic configurations, it's going to be confusing to write a 1-2 and then dash plus 4 or plus 1. So to simplify it and to make it easier to understand, we assign letters to these numbers of L. All right? So zeros are S's, 1s are P's, 2s are D's, and 3s are F's. And believe it or not, that's as high as you need to go to fill the periodic table. Okay, so the lowest energy level would be this one, 1, and the only available, this is, let's see, this is a shell. Some of your books say shell, subshell, and orbital. So if the shell is 1, that means that you can only have 0, right? Because n minus 1 is 0. That's as far as you can go. And this is an S. So 1s is your first and lowest energy level. And then if it's 0, then you can only have 0, right? Minus 0, 0, and plus 0. Just 0. So each one of these then can have a plus 1/2 or a minus 1/2. That means you can only have 2 electrons in that orbital. That is it. And that's where hydrogen and helium reside. The lowest energy levels for the fewest number of electrons is that for the ground state. Okay. So I'm not going to spend a lot of time on this because I think we can do the calculations and say what's the number of orbitals that are possible for the N1 level? Well, there's only one, right? We just showed that. There's only one possibility. For the 2 level, right? For the 2 level, you can have 0 and 1 for L. So you can have an S and you can have a P, 0 and 1. Well, how many can you have here? Well, you can have only 1 orbital for that one. But the P, being 1, can be minus 1, 0, plus 1. It can have 3. So what's the total number of orbitals at n equals 2? 4. 1 and 3 is 4. Right? And if you can have 2 electrons in each of these levels, then 3 times 2 is 6. So you can have 6 electrons in the P's. Okay, so we can go on and on with that. And I think if you work some of the problems, then it'll start becoming obvious. All right, for the principal quantum number n equals 3, determine the number of allowed subshells. Principal shell, how many L's can you have for 3? Well, we did that one already, right? 3. You can have 0, 1, and 2. You can have 3 subshells. Okay? All right. We could go on ahead and do this. 3s, 3p, 3d. 1, 2, 3 subshells. How many electrons can you have? Well, you can have 2 here and 6 here. We already did those. But how about the d's? Well, the d's are 2, right? So 2 is going to be minus 2, minus 1, 0, plus 1, plus 2 with 2 electrons each. So 2, 4, 6, 8, 10. D's can have 10 electrons. Okay? Now, while you're doing this, if you look at the periodic table, and we're going to show you a diagram in a second, but I think it's illustrated now. If you look at the 2 left-hand groups, the alkaline metals and the alkaline earths, then you've only got 2 columns. That's because that accounts for the s orbitals. 2 electrons. 1 electron in the first column, 2 electrons in another column. If you go over to the right, where it starts with boron, aluminum, gallium, and then you move next, carbon group, pnictogens, chalcogens, halogens, you're talking about p orbitals over there. And in that case, you need 6, right? So boron, carbon, nitrogen, oxygen, fluorine, neon, 6. Right? So the far right-hand side is p orbitals, 6 electrons. If you go in the middle, transition elements, you'll find that between, after you pass calcium, you got scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. That's 10. you're filling d orbitals in the transition metals. Okay? So I hope you're getting an idea that the periodic table is arranged that way for a purpose. It's showing you which orbitals are being filled as you build atoms and put electrons into them. Okay, for L equals 2, here, determine the magnetic quantum numbers and the number of orbitals. Well, the magnetic quantum numbers will be 2, 1, 2, 3, 4, 5. You got 5 orbitals. Okay, those are the numbers. All right. Notice that for all of these s orbitals, 1s, 2s, 3s, right? Shape. They're all s's, which means they're all spherical. They're round, but they're not exactly alike. The 1s is virtually solid. The 2s is like a solid within an annular ring of some kind. It's more like a hollow sphere. And notice that white region in there, right there. That says that the equations predict that there is no probability of finding an electron in that region. And that's a three-dimensional region. That's called a node. So, if the principal quantum number is 2, then you're going to have one node. If the principal quantum number is 3, then you're going to have 2 nodes for the s orbitals. For the p orbitals, they look a little different. They're kind of like dumbbells, or I don't know, funny looking eggs. But you can have 3 of them, right? You can have 3 for the p's. Sometimes we call them x, y, and z. But p is 1, so you can have -1, 0, +1. So this would be -1, 0, +1, right? And the magnetic quantum number here tells you orientation. So this is the easiest one to understand. One of them is going to be oriented on the x-axis, one's going to be on the y-axis, and the other's on the z-axis. That tells you orientation. The d orbitals get a little ridiculous. There are 5 of them, which is correct. 1, 2, 3, 4, 5. But they have different shapes. They're kind of a more complicated dumbbells. Right? You got these first 4 are easy to understand. They're dumbbells and they're oriented differently from one another. This last one is kind of weird. It's got a donut in the middle. And then the F is even worse. How many orbitals are F? 7, right? If F is 3, then you can have -3, -2, -1, 0, +1, +2, +3. 7 M sub L numbers. All right. And then the electron spin is fairly easy to understand. Think of it as spinning tops. Now we have some guideline principles that we need to follow when we're building atoms so that we don't violate any physical laws. The first one is the Pauli exclusion principle, named after Pauli. What he said was, in any given atom, no 2 electrons can have the same set of 4 quantum numbers. They can have the same n number, they can have the same L, N, L, M sub L. If they do, then they have to have different spins on the electrons, the 2 different electrons. They could have any other combination, but they cannot have the same set of 4 quantum numbers. That's the Pauli exclusion principle. Now the problem arises when we start to try to understand energy levels, like I was talking about before with the Heisenberg exclusion principle, uncertainty principle, excuse me, the Heisenberg uncertainty principle was that these energy levels are not fixed. These energy levels are influenced by both the number of protons in the nucleus and the number of electrons. Polyelectronic atoms have all these negative charges out here, and they naturally have repulsive impact on each other. The protons draw them in, but they repel one another. So the energy levels are not fixed. They're generally in the same region for any two different elements, but they're not exactly the same. And it's because you have all these repulsive forces acting in that electron cloud. And this illustrates some of those differences. In other words, you might see 1s at this level, 2s at this level. We would expect, because 2 determines the energy, that the 2p and the 2s would be in the same region, right? But if you start putting electrons into the 2p, then it pushes its energy up higher by repulsion. So you get 2p a little bit higher energy than 2s, and then you have 3s, and then 3p and 3d are a little bit higher energy, and then you get to 4s. And it, in fact, under certain circumstances, in fact, actually, when you're starting to fill the elements, this 3d should be higher than 4s, right? So that effect can shift this relationship. You would expect 4 to be a higher energy than 3, but 3d is a higher energy than 4s, right? And I'm going to show you how to deal with that when we start building atoms. One other effect, the penetration effect. All the penetration effect says that the probability of finding electrons in certain regions of space is responsible for the predominance of energy assigned to a given orbital. And it's best illustrated with a diagram. So here you have the level 2, n equals 2, and you have the s orbital described and the p orbital described. So the probability of finding electrons close to the nucleus for the p looks to be better than it is for the s. But the difference is that this 2, remember, has one node. It has a node here, and it has electron distribution that's much closer to the nucleus than the p. That penetration effect gives the 2s orbital overall a lower energy profile than the 2p. And this is all theoretical, right? I mean, it's backed up with some experimental evidence, but these probabilities are derived from, actually not, excuse me, I said Heisenberg earlier. That's wrong. Schrodinger wrote the first equations for the quantum mechanics. I'll have to put that in the, when I process the video, I'll have to make a comment at the bottom. So I misspoke with Heisenberg. It was Schrodinger that wrote these equations. Okay, here we've got a 3s orbital. It has, most of its probability is further from the nucleus, but it has a significant contribution from these two humps closer to the nucleus with, remember, 3s, 3, 2 nodes. So there's a node and there's a node. Now, if we compare the orbitals within the 3, n equals 3, we find that the 3s has a significant penetration close to the nucleus, which makes it less energy than the 3p, which also has a contribution here. And then the 3d, which has no nodes, and its most contribution is out here. So you would expect that based upon the penetration effect, the 3s is lower energy than the 3p, which is lower energy than the 3d. Okay, now let's talk about the periodic table. Now that we know how to build, well, we haven't practiced it a lot, but we know the fundamentals of building an atom with its electrons. We need to talk about the periodic table because the periodic table is structured the way it is to help us understand the nature of each element. And that is in reference to its electronic structure. Okay, historically speaking, in the late 18th and early 19th century, it was noticed and published by Johann Dobereiner that there were groups of elements that behaved similarly. He called them triads because there were only 3 elements that he put together at any one time. One example of that is the halogens, chlorine, bromine, and iodine. They have similar behaviors, and he grouped others in triads, but that's as far as he took it. He didn't go any farther with it, right? So it was later that a German and a Russian, Julius Lothar Meyer and Dmitry Mendeleev, noticed that elements could be grouped in families, right? Actually, Mendeleev put the families horizontally at first in his first publication. In the second publication, he rotated them because it worked better. But they noticed that this family arrangement, and then they also noticed that when they put them in families like this, and these elements all had similar behaviors, similar properties. They weren't exactly the same. They were family members. Right? There were some differences. That if you follow across at this level, right? You have an element here and an element here. Well, this one's different than that one, but it's bumped up by 1 proton. Then you keep going and you keep going and you keep going, and eventually you come out here and you say, okay, we got this one that we keep going, but this one looks an awful lot like that one. So we just swing around and put it in this group right here, right? Because it's similar to those. That's a period. A period, when you go to the end and you rotate and you go back, start over again. It's like periodic motion. You know, when a pendulum moves, right? What does a pendulum do? It swings, right? Periodic motion is motion that starts from one place, goes through a cycle, and comes back to the same place. That's what's happening here. We're going through a period. We're going down here, then we're starting over again. Going down here, starting over again. That's a period. So, both Meyer and Mendeleev produced charts of elements, but Meyer stopped short. What Mendeleev did was he looked at the physical and chemical properties of the elements, and he said, okay, we know all these elements, but maybe we don't know all of them. And if I put them where I think they're supposed to be, I come along, there's one here, and there's one here, but wait a minute. The next element that we know, the next largest element in mass, if we put it here, it's not going to be like the members of that group. It's more like the members of this group. So I put it over here. And I leave this one blank. And that's not where he stopped. He actually said, okay, one of these days, somebody's going to find an element, and it's going to fit in that slot. It's going to have this mass. It's going to have these physical and chemical characteristics. And he did that for several elements. That's why he gets credit for the periodic table, because he actually predicted the existence of elements that had not been discovered. And he also gave credit to Avogadro's student, Cannizzaro. I think I've told you this story before. It was Avogadro's work and Cannizzaro's publications based on that work that allowed us to determine accurate molar masses. Okay, so once Mendeleev had this information at his disposal, then he could accurately position the elements based upon their mass, and in that order, and with his knowledge of their similarities, he was able to put them in the correct place. Okay. So that was just the beginning of the periodic table. You'll notice, and if you did the extra credit for the periodic table, you'll know all of this, most of this stuff already. Some of these groups have names. Alkaline metals is the first one, alkaline earths, transition metals. Then you have, well, the boron group doesn't have a special name. The carbon group doesn't have a special name. Then you get to the pnictogens, the nitrogen group, and the oxygens, the chalcogen group, the halogens group, noble gases. Down here, the lanthanides and the actinides. The table is also divided into metals and nonmetals. You already know that. And the dividing line starts here underneath boron and above aluminum and zigzags down like that. And notice that some of these are kind of a bluish color. Those are set apart as metalloids. Under certain circumstances, they behave as metals, and others they behave as nonmetals. And they're very, very important to the semiconductor industry because we can manipulate their reactivity as metals or nonmetals based upon their neighbors. Oh, okay. Let's see, where was I? Okay. Well, it's not responding. Well, you have to do it manually to get it going again. Okay. I mentioned various principles that we were following, the Pauli exclusion principle. Then there's one called the Aufbau principle. I don't know German, but near as I can tell, Aufbau means do it this way. What it means is that the order that electrons enter an atom as you're building larger and larger elements, the order is in the next electron goes into the next available lowest energy state. That's the principle. And our example here is oxygen. If you write oxygen in its electronic form, using our shorthand, what we need to know is how many electrons are in oxygen, right? 8 electrons. Because it has 8 protons, the neutral atom has 8 electrons, right? So they go in order, lowest energy to highest energy. Lowest energy is 1s, then 2s, then 2p, then 3s, then 3p. Okay, that's probably more than we need. But what's the maximum that can go in the s orbital? L equals 0, 2 electrons. What's the most that can go in s? 2 electrons. What's the most that can go in p? 6 electrons. But 6 will give us too many, right? 6 plus 2 plus 2 is 10. We only need 4 electrons to go in there. Right? So now we're filled. Okay, Hund's rule. Hund's rule says that when we put electrons in there, if there are sublevels, like this doesn't have a sublevel, this doesn't have a sublevel. If there are sublevels, like this one, right, 3, -1, 0, +1, or XYZ. These 4 electrons, they have to go in first like this, spin up, say +1/2, +1/2, +1/2. They have to be unpaired until you run out of room, and then you go back and put the 4th one in. You can only pair them up after all the sublevels are filled with a single spin. That's Hund's rule. Now, he just didn't pull this out of thin air. There's experimental evidence for it. And I don't think we talk about that until the 2nd semester. So whatever you learn in this chapter, don't forget it if you're going to come back for the next semester. Now, this orbital diagram is okay, but it's a little bit too much work for me. Drawing boxes and double-headed arrows. I like lines and single bars. It's a lot quicker, and it gives you the same information. Now, what's a valence electron? Technically speaking, a valence electron is the outermost electrons in an atom that are also available for bonding. That's valence as opposed to core. Core electrons are not available for bonding. Only valence electrons. And the valence electrons are all the electrons that have the same principal quantum number. So for this one, you've got quantum number 2, you have 6 valence electrons. Okay? And here was what I was explaining earlier. The periodic table is arranged so that we can tell which orbitals are being filled as we move through a period and then circle back and start over again. If you're in these first 2 groups, the alkaline metals or the alkaline earths, only s orbitals are being filled. So the first group, you've only got 1 electron in that s orbital. Second group, you've got 2 electrons. The s orbital is filled. And if you move across to the p orbitals, notice the periods here. Period 2, 2s and 2p. And then 3, 3s and 3p. But when you get to 4, now you start getting into the possibility for d orbitals. And the d orbitals are based upon the level above. So you go 4s and then you go 3d. And then you go back to 4p. So when you get to the Ds are always 1 principal quantum level below. As you're moving through the period, you fill the 5s's and then you go back to the 4ds. And then you go to the 5ps. Now we've got a diagram in here. I think it's the next slide. That shows you a neat way. Yes, that shows you a neat way to arrange these. You can use it, or you can use the periodic table. If you know how it's constructed, then you don't need this device. But this takes into account the fact that with multiple electrons in that region, you get those repulsive effects, and they elevate the 3D energy level above the 4s. So you fill the 4s before the 3D. So what you do is, let's see. Yeah. You say, what can you have? You can only have a 1s. That's it. You can have a 2s and a 2p. Yep. You can have a 3s, a 3p, and a 3d. Yep, that's true. You can have a 4s, a 4p, a 4d, and a 4f. You can have a 5s, a 5p, a 5d, and you can have a 5f. You can also have a G, but we don't need it. You can have a 6s, a 6p, 6d. I'm going to stop there. You can have a 7s, a 7p. Okay, so when you start filling them, the filling order is diagonal. That one's filled. Come back around. That one's filled. That one's filled. 2p, 3s is next. And then 3p. And then you go to 4s before you go back to 3d. Then you go to 4p and 5s. Then you go to 4d, 5p, 6s. That way you can get them in the proper order of energy so that the Aufbau principle is honored. But if you know how the periodic table is structured, you don't need that. Right? If you know what's where, then you can write the electronic configuration without going to this device. So let's take an example. Let's take sulfur. Sulfur. How many electrons? Well, let's see how many protons first. Sulfur has 16. Right? 16. That means 16 electrons. Okay. Let's write out an empty electronic structure and then fill in the electrons. So you can have 1s, 2s, 2p, 3s, 3p, excuse me, 3p. And then we could go 4s and then 3d. Remember, it switches back. So 16. 2 maximum there, 2 there, 6 there. That's 10. We need 6 more. 2, we need 4 more. Right? So we don't need these. So that should be 2, 6, 10, 12, 16. That's it. That's sulfur. We can even write it shorter hand. Notice that if you back up, 6 positions from sulfur, you go backwards. Sulfur, phosphorus, silicon, aluminum, magnesium, sodium, and then you wrap up to the next complete shell, you get neon. This is complete. And these are the valence. That's sulfur. It has a neon core and a 3s2, 3p4 valence shells. Okay? Let's use that to do barium because barium is a huge atom. Oops, excuse me. Get ahead of myself. So how about barium? Well, barium has 56 protons, which means 56 electrons. I mean, we could write it all out, but shorthand will take us where we want to go to barium, and then back up until you get to a noble gas. And the next available noble gas is xenon with 54 protons and 54 electrons. Okay, what's left over? Well, look where barium is. Barium is on the 6th period, filling the s orbitals. Right? It's in the 2nd column, so it's got 2 electrons in the s's. Okay? So this is barium, a core of xenon and 2 6s electrons. All right? So that's 4 plus 2 is 6. All right? Europium is a lanthanide. It's an inner transition metal. I'm not going to hit you guys with any of the transition metals. All right, so you don't need to focus on these. But we use the same idea, and we back up from europium, which takes us through samarium, plutonium. No, not plutonium. Promethium. Now that's protactinium. And then neodymium and promethium and cerium. And then lanthanum. And then back through barium and cesium to xenon. So that's why xenon is the core here. And then how did we get there? Well, we went through barium, and then we shifted down to the lanthanides and moved 7 positions over. Right? Lanthanum being the 1st position. Okay, so you don't have to worry about those. I'm not going to hit you with those. All right, periodic trends. Let me see. I think we're getting close to the end. Periodic trends. Yes, and then some final thoughts. These are not the only periodic trends that you can develop from the periodic table, but they are major ones. They're very important ones. Ionization energy, electron affinity, and atomic radius. Okay, let's define ionization energy first. Ionization energy, you take the element, the neutral element, whatever it is, and it has to be in the gas state. Then you add energy to it and kick off only one electron. Okay, how much energy does that take? That is the first ionization energy, from the neutral atom to the +1 charged atom with one electron released. How much energy does that take? The example here is magnesium. Magnesium takes 735 kilojoules per mole for the first ionization energy. And notice that this has to be a gas. Magnesium at room temperature and pressure is a solid. So you got to heat it up and make a gas out of it first before you can determine this value. Now, why is that? That's because it takes a lot of energy to get magnesium into the gaseous state before you can even kick an electron off. So if you took the energy required to go all the way from the solid to this state, you would not be talking about the ionization energy. You would be including some physical changes along the way. So you got to get it in the gaseous state first. Then you can evaluate the ionization energy. You'll notice also that you can take this one, still a gas, and kick another electron off. This is the first ionization energy. This is the second ionization energy. And notice it's higher. It's higher because you're trying to remove an electron from a positively charged ion, and it's more difficult, right? There's a strong attraction between the positive ion and that negative electron. So it takes more energy. But we're still, this would be for magnesium, this would be the 3s. This would be the 3s2. Now it's 3s1. We've removed an electron. So now we're taking the 3s1 and going to a 3s0, right? Now there are no electrons in that orbital. All right, so those are the valence electrons. It takes a little bit more for the second one, but notice when you try to take the third one, where's the third one coming from? It's not valence anymore. The third one's coming from the core. And core electrons are very stubborn. They do not want to be removed. It takes a lot more energy, 5 to 10 times as much energy as even the second electron. Well, in this case, the electron right before the core. That's the explanation for difficulty to remove a core electron. Okay, so what are the trends on the periodic table? I wish I had a periodic table here I could use that was on screen, but I don't. So I'm going to draw a generic periodic table. And we'll leave out the lanthanides and the actinides. But the trend is from left to right through a period. From left to right, the first ionization energy increases. Okay? Why is that? Well, it's very simple. You're adding electrons to the same energy level, right? The same principal quantum number. But what are you also adding? As you add electrons, you're adding protons. So the effective nuclear charge is increasing as you go from left to right, which makes it more difficult to remove an electron. Okay? Now, what about going down in a group? Where are the electrons going in? Well, you're getting protons, yes, you're adding more protons, but you're adding more electrons to further and further distances from the nucleus. And what's in between these outer electrons and the nucleus are extra electrons. They produce what's called a shielding effect. So those negatives are kind of sucking up the energy from the protons underneath, and the outer electrons are much easier to remove. So the first ionization energy trend here is to decrease as you go down. Okay, so that means as you go up, you're increasing. So you increase up and you increase to the right. That means from lower left to upper right, first ionization energy increases. Okay? That's the trend and the explanation in one slide. Well, 2 slides maybe. This just shows trends with some anomalies. Notice that as we go across a period, right, these elements are in their order, right? We go hydrogen to helium, and then we go back down to lithium, beryllium, boron, right? I'm reading these up here. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And the noble gases are in red. They're at the peaks here. They take the most energy because the noble gases don't have valence electrons. They're all core. Okay, so notice that we get an increase as we go from left to right, yes. But there are some discrepancies here between beryllium and boron and nitrogen and oxygen. You get a dip. So what's with that? Well, it depends on which one you're looking at. Let's see. If we're going nitrogen to oxygen trend, nitrogen has 7, oxygen has 8. So what's the electronic structure of nitrogen? Well, nitrogen is 1s2, 2s2, 2p3, right? 7. 3, 4, 5, 6, 7. That's nitrogen. Oxygen is 1s2, 2s2, 2p4. Okay? So which electrons are being kicked off with that first ionization energy? Well, look at this. 1, 2, 3. Where are the electrons in here? Hund's rule. 1, 2, 3. They're all unpaired. Whereas oxygen has 4. 1, 2, 3, 4. When you start trying to force an electron into the same orbital with another one, even if it's opposite spin, there is repulsion. So this electron right here will take less energy to remove than that electron from nitrogen. That's why it goes up to nitrogen and then back down to oxygen before it starts up again. Okay, that explains nitrogen and oxygen. But how about beryllium to boron? Well, beryllium and boron are like this. Let's see, beryllium is 4 and boron's 5. Okay, 5. So this is 1s2, 2s2. Is that right? Yes. This one is 1s2, 2s2, 2p1. Okay? This is a lower energy. S is a lower energy than P. But, let's see, am I correct in that trend? Yes, beryllium and boron. We can't explain this with the decrease in energy like beryllium and then down to borons. We can't explain that with repulsion so much. What we can explain it with is this P is actually further out and higher energy than the S, just a little bit. The higher energy of this electron versus that electron is enough to decrease the amount of energy required to remove it. Okay, so it's not so much electron repulsion for this one as it is difference in energy levels. All right. Which atom would require, got half an hour, which energy will require more energy to remove an electron and why? Well, think of the trend. Sodium and chlorine, they're in the third period, both of them. Sodium's way on the left, chlorine's way on the right. The trend is, as you go to the right, first ionization energy goes up. So chlorine should require more energy to remove that first electron than sodium. How about this one? Which of these requires more energy? Well, the trend here, lithium and cesium are in the same family. So as you go down from lithium to cesium, the first ionization energy decreases. That means lithium should require more energy than cesium. Okay? Which has a larger second ionization energy? All right. So now we need to look at these structures a little more carefully to decide which one has the higher second ionization energy. All right, so lithium is 3. Lithium, 3. So that's 1s2, 2s1, correct? And beryllium, we did beryllium just a second ago. 1s2, 2s2. Okay. First ionization energy would do what? Well, it would put a positive charge here and a positive charge there, and it would make this one go away. There are no electrons in that orbital anymore, but there's still one in this one. Okay? That's first ionization energy. Second ionization energy is what? 2 here and 2 there. Okay, we can do that one with a little more energy. But if we do this one, where are we? We're taking electrons from the core. That means this one, second ionization energy, would be much, much higher than that one. Lithium would be much higher second ionization energy because we're dipping into the core. This is an illustration of which ionizations are required to get into the core for these various elements. And they're in order: sodium, magnesium, aluminum, increasing 1 proton each as you go. So you'll notice that with sodium, we get rid of 1 electron, we're immediately into the core for the second one. But magnesium has 2 valence electrons, so we got to get rid of those 2 before we get into the core. And aluminum, we've got to get rid of 3. Silicon, we got to get rid of 4, and so on, before you get into the core. Okay, that was ionization energy. Now let's talk about electron affinity. This one is a little more difficult. It looks like ionization energy, but it's not. It's not even the reverse. We do have to start off with a gas. All right? But now, instead of removing an electron, we're going to attract an electron. Okay? Now, when an electron comes from infinity down to the highest energy level orbital, it loses energy. Right? So when this X accepts an electron like that, it gives off energy. It may be light or it may be heat. I've just drawn that for effect. All right, so what's the sign on the value is going to be negative, because our system is losing energy in order to acquire that electron. Okay, so the more negative the number, the stronger the attraction of the atom for the electron. The more negative, the stronger. Okay, and I emphasize that because of the way the trend is stated. In general, as we go across a period from left to right, the electron affinities become more negative. That is, the attraction is stronger. Okay, more negative means stronger attraction. The electron affinities become more positive going down a group. They may be negative numbers, but they become more positive, toward the positive. That means as you go up a group, they become more negative. So the trend in the periodic table is lower left to upper right, stronger attraction, which means more negative. Okay? We're not going to spend a lot of time on that one. The atomic radius is the next one. There's a difficulty. The difficulty in estimating atomic radius is we don't know where the electrons are. Right? We already said that. The electrons, we have a probability for electrons out here somewhere, but we don't know where they are. And the size of the atom depends on where those electrons are, because the nucleus is just this little P in the center. The electrons are way out here. So we have two possibilities that are generally used to estimate atomic radius. Okay. If we can find out the distance between two atoms in a diatomic molecule, then we take that distance and cut it in half, and that's the radius. Right? It's not the best, but it's the best we can come up with, because we know if they're in a diatomic molecule, they're bonded, which means they're closer to each other than they would be as free atoms, because there has to be some overlap to make the bond. Okay, so how do we estimate these distances? Two types. For metals, we can have pure metal in a crystalline structure, and we can determine by X-ray diffraction primarily what is the distance between the layers, right? So if the layers are on top of each other, like this, and X-ray diffraction comes in here and tells us, we'll get to that in the second semester, tells us the distance between these two, then we can take that distance and cut it in half. And that's the metallic radius. The covalent radius is more like the one I talked about earlier. When you have diatomic molecules of any of the elements, and these are primarily non-metallic elements, then you can determine the size using X-rays, electron diffraction, neutron diffraction, microwave spectroscopy, or a combination is usually the best way, and sort of average the results. Once you find the covalent radius, then you cut that in half, and that's your atomic radius. Once you find the covalent distance between the nuclei, then you cut it in half, and that's your covalent radius. Okay, so what that tells you is, if you look up in reference manuals or in textbooks or wherever and find lists of radii for atoms, they're going to vary all over the place. It just depends on which ones the author prefers to use. What we're interested in is the trend. Right? So the trend in atomic radius from left to right is the radius decreases. Right? So the radius gets smaller. Why is that? Well, you're adding electrons in this energy level. That doesn't change. But while you're going from left to right, you're adding more protons. you got more positive charge in the center of that, in the nucleus, and it's drawing on these negative charges more strongly. The increased nuclear charge causes the atom to shrink because it's drawing those electrons in closer. Okay. So from left to right, the radius becomes smaller. From top to bottom, where are the electrons going? They're going into higher orbitals. So even though you're adding more protons, then the atom is getting bigger for two reasons. One, the electrons are going into orbitals that are farther from the nucleus, plus those inner electrons are shielding the outer electrons from nuclear charge. So they have more room, right? They don't feel the positive charge as much. So smaller this way and bigger this way. So smaller this way, right? So smaller this way, smaller that way, lower left to upper right, decreasing radius. Okay, that's the trend. And this is a representation. Notice that they excluded the transition metals because the transition metals, they're mostly pretty close together. Plus they do some ups and downs. So they kind of mess up the trend, right? Lower left to upper right works as long as you're with the representative elements. The first two groups and the last six. Okay, which should be the larger atom, sodium or chlorine? Sodium. Sodium is much larger than chlorine because it's far to the left. How about this one? Lithium and cesium. Which one is the larger one? Well, cesium, of course. It's down below. Lithium is smaller. It's up above. All right. Now we're getting pretty close to the end. The point of this concept check is to emphasize the fact that 1s around one atom is not necessarily the same as 1s around another atom. Right? 1s around hydrogen has one proton and one electron. But lithium has three protons. And a 1s orbital with, it happens to have two electrons in it. But what's the size of the, right? What's the size? Remember, 1 represents the size and the energy. But the difference is this one has one proton pulling on that, whatever's in that orbital. This one has three protons pulling on those two electrons. This one's going to shrink more. This one has the bigger 1s orbital, right? The hydrogen, which is lower in energy, right? Lower in the energy is this one because it's closer. This one's bigger, it's further out, higher energy. This one's smaller, closer in, it's lower energy. Okay? Okay. Let's organize the oxygen, fluorine, and sulfur according to their ionization energies. So let's see where they are on the table. Sulfur, oxygen, fluorine, right, in their relative positions. So what does the trend say about ionization energy? Ionization energy says that the ionization energy is going to increase this way and increase that way. So it should be sulfur. Let's see, does it say increasing ionization energy? So sulfur increases, oxygen increases, fluorine increases. It should be in that order. Sulfur, oxygen, fluorine. How about atomic size? Atomic size is just the opposite. It's decreasing size in this direction. So it should be fluorine, oxygen, sulfur. Okay? All right, these are final thoughts, and they just rehash everything we've talked about so far. I'll leave them up there long enough to get them in the recording, but we don't have to talk about them. And that's it.